This is part 3 of my lecture on non-parametric statistics, and I'm going to be talking about tests for comparing two paired samples. The test that I'm going to talk about is Wilcoxon's matched pairs signed rank test. It's a two-sample test, and it requires quantitative data, just like the single-sample Wilcoxon's test, because we have to take a difference between numbers, so we need values that are at least on an interval numeric scale. But it doesn't have to be normally distributed. It's used to compare two matched samples, just like we talked about in the previous lecture, a paired t-test, which was for matched samples. This is another test for matched or paired samples. The null hypothesis is that the differences between pairs of measurements have a mean of 0. In other words, if we take each pair of measurements, they're the same as each other, but not necessarily the same as other measurements in the samples. So the way we do this test is simply to take the difference between pairs of measurements and then apply Wilcoxon's one-sample test, assuming a mean of 0. So the procedure is exactly the same as the Wilcoxon's single-sample test after we've taken the difference between the pairs of measurements. So we can apply it to some hypothetical data, for example looking at metastases. The question that we might ask ourselves are bone scans better than CT for detecting metastases? Our experimental hypothesis, H1, is that bone scans detect more metastases than CT. The null hypothesis, bone scans don't detect more metastases than CT. Note that's a one-tailed test because we're only looking for a difference in one direction, that bone scans are better than CT, not that bone scans are different from CT, either better or worse. We're hoping that bone scans will be better than CT at detecting metastases. Here I have made up some data to illustrate this. It's the number of metastases seen on bone scans and on CT for 15 hypothetical patients. And I've tabulated the data here. Here, for 15 patients, I've shown the number of metastases seen on a bone scan and the number of metastases in that same patient on CT. Clearly these are paired results because each patient has their own bone scan and their own CT. So we take the difference between the number of metastases on the bone scan minus the CT. So the first patient had 0 metastases seen on the bone scan and 0 on the CT, so the difference is 0. The next patient had 1 metastasis on bone scan, none on CT, so a difference of +1. In fact, most of those differences are positive apart from patient 10, who had a negative difference. So we might suspect that because they're all in one direction, that seems to indicate that bone scans have detected more metastases in the CT, but we want to prove it. So the first question is, can we use a parametric test? To use a parametric test like the paired t-test, these differences would have to be normally distributed. Well, here's a frequency distribution of those differences, and if we believe this is normally distributed, we could use the paired t-test. If it's not normally distributed, we have to use a non-parametric test. Well, for normally distributed data, we'd expect a peak at the center and tails coming out equally on either side. This data seems to be peaked rather at low values with a tail off to the right. So probably we should be cautious and use a non-parametric test. Actually, if we use a non-parametric test, we could do it even if the data was normally distributed, but if the data is normally distributed, it would be more powerful to use the parametric test, which will be the t-test. We've got two paired samples. We know that the data are quantitative, and as I've already said, if the distribution of differences was normal, we would prefer to use the parametric test, which is the paired t-test, but if we believe it's not normal, we'll use the non-parametric test, which is Wilcoxon's matched pairs sign rank test. Well, at least for the purpose of this exercise, we better believe it's appropriate to use the non-parametric test, otherwise there won't be much point in me illustrating this data. So here are the numbers again. We've already calculated the difference between bone and CT, and now I've added 2 extra columns to show the sign of the difference, whether it's positive or negative, and in fact they're all but one are positive, and the magnitude of the difference. Notice that quite a few of these have 0 difference. And the procedure requires that we rank the differences in order of magnitude, ignoring sign for the moment, and that we ignore all the 0 differences. So there are 5 patients here where there is 0 difference. When we come to look at the ranking, we ignore those 5 patients. So this is the ranking of the remaining 10 patients, and patient 2 has 1 with a positive sign, patient 9 has 1 with a positive sign, patient 10 has 1 with a negative sign, and patient 14 has 1 with a positive sign. So those 4 patients who have a magnitude of 1 would have ranks 1, 2, 3 and 4, but they're all tied, and so according to our rules the average of 1, 2, 3 and 4 is 2.5, so we give them each the average rank of 2.5. Patient 1 had a positive sign, and so their rank of 2.5 goes in the positive sign column. The same with patient 9 who had a positive sign. But patient 10 had a negative sign, so their rank of 2.5 goes in the negative column. Once again, when we get to patients 4, 7 and 15, they all had a magnitude of 2, so they would have ranks of 5, 6 and 7, but because they're tied, we give them all the average rank of 6, and as it happens they're all positive, so they all go in the positive sign column. And then patients 12, 13 and 15 have ranks 8, 9 and 10, and they're all positive. So the next step is to add up all the negative ranks. There's just one, it's 2.5. All the positive ranks, if you add those up, they come to 52.5. Clearly those look quite different, but we now need to just test, is that significant? So we need to go to our tables. We've got a sum of negative ranks of 2.5, a sum of positive ranks of 52.5, which means that the sum of all ranks would be 55. Remember that we started with 15 patients, but we had to ignore 5 who had 0 difference, so we've just got a sample size of 10 remaining. If we look at the row corresponding to a sample of size of 10 in our table of the critical rank sums for the one sample Wilcoxon test, then we see that the expected sum is 27.5, which tallies with our measurements because we've got a total rank sum of 55 and the expected value should be half of that, which it is. Now remember we're doing a one-tailed test, so we have to look at the possible significance levels. P of 0.025 one-tailed gives us a critical sum of 8, and P equals 0.005 one-tailed gives a critical sum of 3. Now we take the smaller of our rank sums. The smaller of 2.5 and 52.5 is clearly 2.5. So that is both less than 8 and less than 3. So we have a result that is significant not just at the P equals 0.025 level, but the P equals 0.005 level as well. Remembering that for the Wilcoxon test, the rank sum has to be smaller than the critical value to be significant, meaning that it's further away from the expected value, which was 27.5, so it's more extreme than the expected value. That's why it's significant. So a significant result, we can reject the null hypothesis, which was that the bone scan and CT were equally good at detecting metastases, so we have to accept the experimental hypothesis that bone scans are better than CT at detecting metastases, at least for this hypothetical data that I've made up for the purposes of this illustration. Whether it's true in practice or not is another matter. So there we've seen another example of how we can use a non-parametric test for a realistic sort of calculation. And once again you've seen it doesn't involve any really difficult mathematics. It's just a question of writing things down in the right order and a little bit of addition.